Hello, everyone. Today we are going to finish section 2.3 and learn how to build inverse matrix and also how to use Cramer's rule to solve linear systems of equations. We are going to start with inverse matrix. Let's remind you what we've learned so far. So far, we learned a big theorem, which was determinant of the product of matrices A and B equals product of determinants of matrix A by determinant of matrix B, right? So that was the first theorem we learned. We labeled it theorem. Another theorem, which was one of the consequences of this theorem, that if the matrix A has inverse, then determinant of A multiplied by A inverse, we know that A multiplied by A inverse is going to give us identity, right? So determinant of A multiplied by A inverse is going to be what? Using the product theorem, it's going to be determinant of A by determinant of A inverse. And on this side, determinant of identity matrix is equal to 1 because it's all diagonal elements are equal to 1, from where we can say that determinant of inverse matrix equals 1 over determinant of matrix A, right? Basically, this is one of the theorems I was asking you to prove, please. Now, how are we going to use these facts? Well, first, before we start developing anything about inverses, I want to remind you a couple of facts about just normal determinant. The first fact, we learned that if matrix has two same rows, the determinant is going to be equal to 0. Remember this? There was a theorem, I don't remember the number, but if A has two same rows or columns, the determinant A is equal to 0. Well, we were proving it by interchanging actually two same rows, and we know that from interchange, determinant is supposed to change the sign. On the other hand, change of two same rows is going to change nothing. So, which means that determinant of A is going to be equal to determinant of 2 minus determinant of A, which can be true only if determinant of A is equal to 0. One thing related to this fact is next. Remember, cofactor expansion of the determinant of the matrix, not using Gaussian elimination, but just cofactor expansion. Remember, if you have a matrix which consists out of certain rows and columns and all of them, how do we expand it by the first row? We are going to, let me put one more element over here. We're going to multiply elements of the first row by cofactors of the same row. Let me remind you, cofactors are determinants of the matrix which you get while you are crossing a certain element. For example, for A11, cofactor is determinant of the matrix which is left over after you cross element A11, the row and the column of A11. It's also going to be multiplied by either +1 or -1 using the checkerboard rule, right? So let me continue and write down some more cofactors. So element by corresponding it to cofactor, element by corresponding it cofactor, and so on. Now, guys, question. If I multiply cofactors of the first row by any other row, for example, if I multiply cofactors of the first row, like C1, 2, C1, C1, 1, C1, 2, C1, 3, by the second row, for example, A 2, 1 by C1, 1 plus A 2, 2 by C1, 2. So I take cofactors of the first row, but instead of the elements itself, I'm going to put elements from the second row. What is going to be the result over here? Well, for us, it's going to look like somebody took the determinant of the matrix and expanded it by the first row because these are cofactors of the first row. But because we multiply them by the second row, it's going to look, when we kind of go backward, if you go backward to the matrix, like you have cofactors of the first row, but instead of the first row, you have over here second row. And it's going to look like you calculate the determinant of the matrix with two same second rows, which is going to be equal to 0 because of this theorem, right? So actually, this is interesting fact that if you take cofactors of one row, like first row or second row or third row, and multiply them by any other row except its own row. So if they're cofactors of the first row, if you multiply them by elements of any other row, like second row or third row or any other row, for us, it's going to look like you calculate the determinant with two of the same rows. If you multiply them by elements of the second row, it's going to be like two second rows in the determinant, which is going to be 0. And for all other determinants is going to be correct. So if cofactors of the first row are multiplied by anything but the first row elements, the determinant is going to be kind of equal to 0, or this sum is going to be equal to 0 because this sum is actually going to be the determinant. So this is first fact. We are going to use it to kind of prove something for inverse. The second fact, let me remind you how inverse matrix of 2 by 2 was looking. Do you remember the formula for inverse matrix of 2 by 2? I'm going to just briefly refresh it. Inverse of 2 by 2 matrix. 2 by 2 matrix. So imagine that we have 2 by 2 matrix, and it's going to be A, B, C, D, right? How inverse is going to look. We know the formula for inverse, right? Well, we can do it by Gaussian elimination and bring it to identity, but we also know the formula for 2 by 2 matrix is going to be like 1 over A by D minus B by C, and multiplied by the matrix where you switch the diagonal elements. You put over here element D and over here element A, and put minus in front of non-diagonal element, right? That's how we build inverse matrix of 2 by 2. Now, we are going to kind of prove the theorem about like how to find inverse by the formula for any matrix. After we did this kind of little review, we scroll it up. I'm going to bring it back later. But for now, guys, we're going to do a couple of definitions. So definition number 1. If you have matrix A with elements A1, 1, A1, 2, and so on, and here A2, 1, A2, 2, and so on, and lots of other elements, then we are going to have cofactor matrix. Cofactor matrix. Guys, I'm going to call it C matrix. Actually, I don't think that we have a special name for it, but the matrix which is built out of cofactors to certain element. For example, the first element of cofactor matrix is going to be cofactor of element A11. Means that you cross out element 1, 1, you are going to get the determinant of the matrix, which is smaller, and multiplied by plus 1, right? Actually, cofactor C11 is equal to what? Minus 1 to the power of 1 plus 1. And then the determinant of the matrix A22, A23, and so on. And like, okay, the whole bunch of these elements. So we are going to put cofactor 1, 1 here, cofactor 1, 2 here, and this is going to be cofactor of element 1, 2, and so on. This is called cofactor matrix. Maybe as example, let's find the cofactor matrix for matrix 2 by 2. Let's imagine that we have matrix A, which is just 2 by 2, A, B, C, D. What is going to be cofactor matrix for it? Well, cofactor matrix is going to be first element is A. If I cross it out, the only leftover element is D, right? And because determinant of matrix of 1 by 1 is just element itself, so I'm just going to put element over here. Now, if I cross element B, cofactor or remaining matrix is just C, right? So I'm going to put over here C. The checkers rule is going to tell me that the first element was plus and the second element was minus. So I'm going to put minus here. For element C, what is going to be cofactor? Cofactor for element C is going to be element B. It's going to have minus because of the checkers rule, plus, minus, plus, minus. And for element D, cofactor is going to be, if you cross element D, it's going to be element A, and we are going to have it with plus. So this is cofactor matrix for matrix A. We're going to have plus. Plus, minus, minus, plus. Now, next definition. So this is how we build cofactor matches. For bigger matrices, we instead of just elements, we are going to have determinants of smaller matrices, like shorter ones. Like if it's 3 by 3 matrix, so here we are going to have determinants of 2 by 2. Second definition. Adjoint matrix. Which is denoted like this, is going to be a transpose of cofactors matrix. For example, what is adjoint for this matrix C? Not for this matrix C, but for matrix A, which is like, what is transpose of this matrix C? Remember how we build transpose. I'm going to build transpose of C. So supposed to be C transpose. And what is transpose? We just take rows and turn them into columns. So it's going to be D minus C. D minus C here. And the second row is going to become a second column minus B and A. Well, guys, you probably see where I go now. If you compare it to the formula of inverse matrix of 2 by 2, you see that it's almost inverse matrix of 2 by 2, right? It's D minus B, D minus B minus CA, exactly. The only missing thing over here is 1 over this AD minus BC. What is actually AD minus BC for matrix 2 by 2? This is determinant of matrix A, actually. Well, for 2 by 2, it's going to be literally AD minus BC, but for bigger matrices, it's going to be more complicated. So what does it mean, guys? It means that actually inverse matrix can be built using this adjoint matrix. So the only missing thing to build inverse for 2 by 2 matrix is to have 1 over determinant of A. And that's going to be the rule for bigger matrices too. So A inverse is going to be adjoint matrix of matrix A divided by determinant of matrix A. For 2 by 2 matrix, it's working because for 2 by 2 matrix, as example, we are going to have what? Adjoint matrix is D minus B minus CA, and determinant of matrix A is 1 over what? AD minus BC, right? So for 2 by 2 matrix, everything works perfectly. Now we are going to prove that it's not going to work only for 2 by 2 matrix, but it's going to work for any other matrix. How are we going to prove it? Remember that to prove that certain matrix is inverse of matrix A, we'll need to multiply them and get identity. Before we proved a very important theorem, we had to do it twice, multiply it from the left and multiply it from the right. But then we proved a little theorem, and now we can just multiply it on one side, either left or right. If you multiply your suggested inverse by your matrix A and you get identity as a result, then you don't need to do second multiplication. You just say that, yes, it's inverse. So basically, guys, what we'll need to prove? we are going to show or prove or kind of prove the theorem. We're going to prove that A multiplied by A inverse equals identity. So we're going to prove that if you build inverse matrix by this formula, then you are going to get identity. Okay, let's do it. Actually, we are just going to show it literally by multiplication. And again, inverse matrix here is a joint matrix divided over determinant of A. Well, I'm going to write down everything what like in terms of this adjoint matrix and determinant, and I'm going to have matrix A. I'm trying to say what I'm proving, and then adjoint of A, and then divided over determinant of A. Supposed to be equal identity matrix, right? Well, guys, I want to multiply both sides of this expression by determinant of A and prove actually that A multiplied by adjoint of A, this weird matrix which you get from cofactors, is equal determinant of A multiplied by identity. Determinant of A is just a number, like, usually we get like minus 22 or 6. So I can multiply by this number both sides of my true statement, and still that statement is true. I'm going to prove that this one equals to this. And then we can move determinant to the left side and show that it's identity. How I'm going to do this? Well, I'm going to start with writing down, sorry, I wanted to write down actually the expression for it. So I'm going to consider A multiplied by a joint matrix of A. I'm going to literally write it down to the elements. A11, A12, A13, here A21, A22, A23, and lots of elements. This is my matrix A. What is my adjoint matrix? Well, it's built from cofactors, right? But because I'm supposed to kind of turn cofactors into transpose to get adjoint. So normally I have cofactors of elements 1, 1, 1, 2, 1, 3 over here. So C11, C12, C13. This is going to be cofactors matrix, but because I'm supposed to turn it into adjoint, I'm supposed to take a transpose of it. So it means that I'm going to actually have this C12 over here. C12 and C13 is going to be like, well, because adjoint is not just cofactors, it's a transpose of cofactors. Sorry. Adjoint is C transpose, cofactors transpose, C13 and so others. And here are going to be some other elements. What is going to happen when I multiply them? Let's just kind of perform multiplication. Remember, by multiplication rule, we multiply the first row of my first matrix by the first column of your second matrix. Let's multiply it somewhere side before we put element into the resulting matrix. So what we have? A11 by C11 plus A12 by C12 plus A13 by C13 and all other elements. So you see that you multiply cofactors of the row number 1 by row number 1 elements. What are you going to have? You are going to have determinant of matrix A. So my first element is determinant of matrix A. Now, what is going to be my second element? Second element is a second row by the first column. I'm not going to calculate all of them, just you will understand the idea. I'm going to have A21 by C11 plus A22 by C12 plus A23 by C13 and so on. I'm going to have cofactors of the first row multiplied actually by the second row. Remember, I was telling you what is going to happen if you multiply cofactors not by the row they belong to. The determinant is going to be the determinant, but it's going to be the determinant of matrix with 2 second rows. And we remember that it's going to be equal to 0. So element is going to be 0 over here. What is going to happen to the next element? Well, next element is, again, that's going to be row number 3, but cofactors of element of row number 1, 0 again, and all of them zeros. So what is going to happen over here? Well, over here, guys, we are going to have cofactors of the second row multiplied by the first row, of course, 0. But when you have this element, which is 2, 2, we are going to have second row by cofactors of the second row. And these two are going to be just expansion of the very same determinant by the second row. And we are going to have, again, determinant of A. You see what we have? Diagonal elements which have matching row and cofactors column are going to be determinant of A. Everything non-diagonal is going to become 0. And eventually, the matrix we are going to have is going to be almost identity, right? But identity, like you multiplied identity by determinant of A. So why don't we take this determinant of A outside of identity, kind of outside of each element over here, and put it in front? We are going to have determinant of A. And now left over is going to be 1 here and lots of zeros here, and then 1 here, and 0, 0, 1. And what is going to be over here? It's just identity matrix. Let me make it a little bit smaller so you can see the whole thing. So what we have over here is determinant A by identity. And that's exactly what I was saying I'm going to prove, that A by adjoint equals determinant of A by identity, which means that if I divide by determinant this side, I'm going to prove this statement that yes, A multiplied by this weird matrix of adjoint over determinant is going to be equal to identity, which means that this one is inverse of A, because it's kind of some matrix you multiply by A and get identity. By one of the theorems we had, this matrix supposed to be inverse. Okay, so we proved the theorem and we developed the rule how we calculate inverse matrix without doing row elimination. I think we can do one example of inverse matrix doing without row elimination, just directly calculating it. It's going to be much longer than row elimination, but we should do it once at least, okay? I'm going to show you the whole procedure of finding inverse matrix. So, let me copy the matrix first. Example. Let's consider matrix A, and it's going to have next terms. 1 minus 2, 0, minus 1, 0, minus 1, and 0, 2, minus 1. So the question is find inverse using adjoint. Okay, I'm going to write down just join the A. How we are going to do this? Well, let's look at the formula for inverse. A inverse is equal adjoint matrix divided by determinant of A. So maybe a good idea to find the determinant of A matrix first, because we'll need a number in denominator anyway, and then we are going to build this adjoint matrix. Well, I don't know. For 3 by 3 matrix, we actually can do expansion by the first row, for example. So determinant of A is going to be 1 by determinant of remaining matrix, which is 0, minus 1, 2, minus 1, right? And then minus, remember plus minus alternation, and then minus 2 coefficient itself. And then what happens if you cross this element out? We are going to have determinant of matrix minus 1, 0, minus 1. Now we just need to calculate it. So I have 1 multiplied 0 minus 2. We are going to have 2, right? Again, 0 by -1, minus -1 by 2, 2. And then minus minus is going to give me plus. And here, -1 by -1 is +1. And this one is going to be 0, right? So what I have 2 plus 2. My determinant is equal to 4. I wanted to write down actually 3, no reason. So I know the first part. I know what is going to be in denominator. Now I just need to build a adjoint matrix, which is not going to be easy because 3 by 3 matrix is going to give you 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. I'm going to start with cofactors matrix. Cofactors matrix is going to have elements C11, C12, C13, C21, C22, C23, C31, C32, C33, and I'm going to just calculate them. They are cofactors of elements of matrix A. I'm going to start with C11. C11 is a determinant of leftover matrix when you cross the first element, right? And I'm going to calculate it C11. So we have, well, checkers rule is plus, minus, so it's plus. And we are going to have matrix 0, -1, 2, -1. The determinant of this matrix is 0, minus, -2. Looks like it's 2, so I'm going to put over here 2. Okay, C12. C12, I need to cross, I'll need to cross element 1, 2, which is like -2, right? And remaining matrix is going to be -1, -1, 0, -1, which is going to give me what? 1. But checkers rule gives me plus, minus, minus. I'm going to put -1 here. Well, let's just calculate all of them, right? The element 0 is going to be multiplied by determinant of whatever left over, -1 by 2, which is going to be -2, -2. And the next element, -1, will be multiplied by, -1 is going to be multiplied by the determinant of 2 -1, which is going to be 2 by -1 is -2, right? Let me just double check. -2 by -1, it's 2. And the minus from checkers rule is -2. In the next one, I cross out 0. I have 1 by -1, which is going to be -1, right? And my checkers rule is going to keep -1 because it's minus, plus, minus, minus, plus. Next element is going to be for -1. It's going to be you cross -1. We are going to get 1, 2, and 0, 2. So 1 by 2 is 2. And 2, I think, supposed to have minus because it's minus, plus, minus. And we have just last row. Last row is going to be 0 multiplied, not multiplied, but just for this. For 0 element, it's -2, -1 is going to be 2. And plus, minus, plus, so it's 2. Next one is going to be element for 3, 2, which is going to be like you cross out this element. 1 -1, it's just -1. And the checkers rule is going to give me 1. And the last element we are very close to is going to be 1 by 0 minus -2 by -1, which is going to be 2. So minus 2 -2 and plus minus plus. I think that's it. Just let me double check the last element because kind of my scratch work has it positive. Maybe I did a mistake somewhere. Let me do one more time. So I cross out -1. We have 1 by 0, which is 0, -2, and checkers rule is plus, minus, plus, minus, plus, plus, minus. Well, looks like it's -2. Maybe I did a mistake. Well, let's kind of agree that it's -2. Okay, so we got our C matrix. Now to get a adjoint of A equals C transpose. So I just need to copy matrix C instead of rows into columns. 2 -1 -2 Next, second row, -2, -1, -2. So -2, -1, -2. And the last row is 2, 1, -2. So it's 2, 1, -2. So now I just need to write down like the formula for my inverse. So A inverse is going to be equal my adjoint of A by determinant of A. And determinant is equal 4, right? So it's 1/4. And I'm not gonna turn in like 1/4 into the matrix. I'm just going to copy the matrix and have this as a coefficient. -2, -2, -2. Well, looks a little bit weird to me, but I don't know, like maybe I did a mistake somewhere while I was calculating. A good chance to check it. Okay, so maybe I'm missing minus from somewhere. That's my inverse matrix, and that's an algorithm of how we find inverse a different way without Gaussian elimination. So first, we find the determinant of the matrix. Second, we find matrix of cofactors. And third, we just transpose it. That's going to, and use known determinant. So that's how we find inverse matrix. Now, second topic of our lecture today is Cramer's rule. What is Cramer's rule? Remember that our goal is to find solution of linear system. So Cramer's rule is going to work with solution of linear system. Cramer's rule. Cramer's rule is solving linear system AX equals B in like n unknowns, and if determinant of A is not equal to 0, and determinant of A is not equal to 0. Guys, I don't want to set up this as a theorem. I'm just going to show like why Cramer's rule is working, and we are going to learn how to just use it. Remember, if determinant of A is not equal to 0, then A is invertible. Means that there is A inverse somewhere, right? We do know actually formula for A inverse now, right? How it helps us to solve the system. Let's write down the system. AX. Our goal is to find X, right? So we have matrix of coefficient A's, and these are unknowns, X's, and this is the right side. How do we find X? Well, remember how we were solving it long time ago, maybe like 3 or 4 weeks ago. We were multiplying both sides of this equation by A inverse because we know that it exists, right? So we do A inverse AX here and A inverse B over here. Well, because A and A are inverses, we are going to have identity X here, A inverse B. And identity by X is going to give us X equals A inverse B. So basically that's a formula we knew already. Today we added to this knowledge of how this A inverse looks, right? Well, let's apply this A inverse as a formula. So A inverse is adjoint of A divided over determinant of A. And we'll need to multiply this thing by B. Let's write it down in the matrix form. Again, I'm going to copy. What are X? X here, it's actually the column of unknowns. X1, X2, Xn. If you do multiplication, ideally on this side, you are going to have column of the solutions. I don't know, like you can label them as A's or like whatever the result of the product are going to be numbers. So let's see how this product is going to be formed. I'm going to take the determinant again, like in front. So I'm going to separate it from the rest. Determinant of A. What is adjoint? I'm going to actually write down. Well, adjoint is matrix of cofactors where cofactors of the first row are actually sitting as a first column, right? And that's what I'm going to do. I'm going to do C11, C12, C13, and so on. So this is first row cofactors, and I put them as a first column. And I'll need to multiply it by the row B1, the column B1, B2, and somewhere here, Bn. How do I calculate x1 here? Give me a second. Okay. You calculate x1 here, my first element. I'll need to take this row and multiply it by this column, right? Which is the only part of the matrix. I'm going to write down that x1, first element, or whatever I get here when I do multiplication, is equal 1 over determinant of A. And here I'm going to have C11 by B1. What I'm going to have as a second column over here, C21, C22, well, a little bit more, C31, C32. These are cofactors of the second row, cofactors of the third row, and so on, right? Going to multiply C21, B2, plus C31, B3, and so on. Well, this is a determinant, but what kind of matrix is determinant? This is going to be like a determinant expansion by, well, this, if I was using C11, C12, C13, that would be determinant of matrix A by the first row, right? But if I'm using C11, C21, C31, that's going to be a determinant of the same matrix A, but by the first column. Because I'm multiplying elements B1, B2, Bn, these are going to be like elements which you put into determinant. So actually this is determinant of the next matrix. Matrix B1, B2, Bn. And here A, well, 1, 2, A, 2, 2, A, 1, 3, and so on. For us, it's going to look like you took original matrix and put this right side numbers, right side column, into the first column of your original matrix. If you do this, then just let's look at this kind of expression. We're going to expand by the first column. We're going to have B1 multiplied by, if you cross B1, by a joint of C11, right? And that's exactly what we have. B1 multiplied by C11 over here, right? And then B2, if we cross it, we are going to have a joint of element C21, which is actually C21. So it looks like we have this one is a determinant of matrix A, but instead of actually the first column of matrix A, you have B1, B2, B3 substituted. So we are going to have then the formula determinant of matrix A1, which is going to be built by taking column B and placing instead of the first column of your matrix A. If you want to calculate x2, you are going to take the same B1 column and put it instead of column 2. So it's going to be determinant of A2 by determinant of A. And this is basically Cramer's rule. Cramer's rule helps us to calculate one solution. You don't necessarily have to solve everything. You can calculate x1 or x2 if you know determinant of matrix A, and you can calculate the determinant of matrix which you build by replacing I row, I column by elements of the column B. Well, maybe it doesn't look very clear what I mean, but that's Cramer's rule. All other elements like, so for xi is going to be determinant of ai over determinant of A, and I'm going to write down AI. It's actually going to be the matrix A, but instead of column I, you are going to put B1, Bn. So everything like A11, all elements of matrix A, except I column is going to be B1, Bn. That's Cramer's rule. I don't think that Cramer's rule is very useful to use on exams because calculating determinants is very time consuming, but we're gonna kind of use it once. Let's imagine that we have a next system of equations. Example. Make my squares a little bit better. My example. Matrix A equals matrix of coefficients 1, minus 2, 0, minus 1, 0, minus 1, 0, 2, minus 1. That's exactly the same matrix I had, for example, over here. Why I'm using that? Because I already calculated the determinant of it. That's 4. Now, the system of equations, again. The system of equations is going to look like this. Matrix A multiplied by x is going to be equal to column of B, which is going to be minus 3, minus 4, and 1. So that's a column. That's my B. And we are going to use Cramer's rule to calculate, for example, x1. So according to Cramer's rule, x1 is going to be determinant of matrix A1 over determinant of matrix A. We already know that determinant of matrix A is equal to 4. Example 1. Let's label example 2. Now we need to find determinant of matrix A1. It's going to be determinant. You take this column, minus 3, minus 4, 1, and put it instead of first column in your matrix over here. Copy the rest. Just calculate the determinant of this. So I'm going to expand by the first row again. And what I have? Minus 3. And the remaining determinant is 0 minus minus 2, which is going to give me just 2. And then minus, plus minus checkerboards, right? And minus 2. And the determinant of the matrix is going to be minus 4 by minus 1, which is 4, right? Minus 1 by 1, minus 1, so plus 1. And I have 6. And here I have 4 plus 1, 5, multiplied by 2 is 10. Looks like I'm getting like 16 as the first element. Oh, I'm supposed to put minus 6 here already. Sorry, guys. I'm missing the first minus. Let me erase everything and just put the minus. Okay, minus 6. So it's 5 by actually 2 plus 10. And that's going to give me 10 minus 6, 4. So my first element is 4. Let's calculate some other elements. No, that's not the first element, actually. I just calculated determinant of matrix A. So I'm going to put 4 here as a determinant of matrix A1, and 4 here as a determinant of matrix A. And my first element is 1, actually. Okay, I'm going to calculate x3. So x3 is going to be determinant of A3 over determinant of A. Determinant of A3, determinant of A3. Well, almost done. It's just the last matrix. So we copy matrix A, 1, minus 2, 0, minus 1, 0, minus 1, 0, 2, minus 1. And then instead of column number 3, we substitute, we erase column number 3 and substitute actually this B row, minus 3, minus 4, and 1. And calculate the determinant. I have, okay, I'm going to expand by first row again. I know that it's not very maybe smart. Maybe I should expand by the last row. Last row is 0 to 1. Why not? Okay, last row. So this one is plus, this one is minus. Minus 2. If I cross out 2, I'm going to get determinant 1, minus 4, and 3, minus 1. 1, minus 3, minus 1, minus 4. I'm going to write it. I'm afraid to lose a minus somewhere. 1 plus 1. And the determinant, if I cross 1, is 1 minus 2 minus 1, 0. 1 minus 2 minus 1, 0. Doesn't look like it's going to be complicated. So what I have, minus 2, and here, minus 4, minus 3 by 1 is just minus 3. I mean, it's going to be 3, but because the determinant has minus, it's going to be minus 3. And the plus 0 minus 2, minus 2. So my result here is minus 2 by minus 7. And here is minus 2 again. So it's 14 minus 2. I think I'm getting 12. So I'm going to substitute this 12 instead of the determinant of A3 and 4 again in denominator. I'm going to get 3. That's my solution, x3. What is good about Cramer's rule? If you just need x1 or just x2, you don't need to calculate x, like other x's. Okay? And that's basically it. So that's how we use Cramer's rule. What I'll need you to learn before the next class is how to build inverse matrix using this adjoint matrix and how to use Cramer's rule. No proofs, just like these two algorithms. Okay. Maybe I did a mistake somewhere when I was doing inverse. You can always check it. I'm going to make it smaller so you can see better like what we did. So basically, I want you to be able to solve problems like examples I considered. Example number 2 and example number 1. This one. Example number 1. So build inverse matrix and be able to use Cramer's rule. For both rules, we're not going to use them a lot, but I want to check that you understand them and at least once you can solve a problem. Okay, that's all for today. And thank you for your attention and sorry for giving you online lecture. Okay, hopefully I'll see you next class in person.